All right, we're going to start chapter 5 today, and that is on analytic trigonometry. And the first thing we're going to go over are the fundamental identities. This is a little bit different than the way you may have first learned trigonometry with SOHCAHTOA, and the representation of everything inside of a right triangle is opposite over adjacent, and opposite over hypotenuse, adjacent over hypotenuse, all those things. This is going to show a lot of times the relationships between the different trig functions. So we're going to go through a bunch of different identities, and you'll see in the next couple sections how we're going to put these into use and basically do transformations that allow you to simplify things quite nicely. So first thing we're going to talk about is the reciprocal trig identities. And so reciprocal, if you think about normally a fraction, the reciprocal of 2/3 is 3/2. So we think we're just flipping the function. And so there are a bunch of reciprocal identities. So for example, the sine of theta is the same as 1 over the cosecant of theta. Those together are reciprocals. So I could also say the cosecant of theta is 1 over the sine of theta. Okay? I could also say that cosine of theta is equal to 1 over the secant of theta. And of course, what goes with that is that the secant of theta is equal to 1 over the cosine of theta. And the last pair of reciprocal identities is that the tangent of theta is equal to 1 over the cotangent of theta, and the cotangent of theta is equal to 1 over the tangent of theta. So there's 6 identities. But really there's only 3 different ones. There's 3 pairs of reciprocals, and so we'd have something like this. Now in your book, in the same green box, they go over the quotient identities, and I've mentioned this in class, and these are important because when I think of tangent of theta, I don't even think of opposite over adjacent anymore. I think of tangent of theta is the sine of theta over the cosine of theta. So this is called a quotient identity because it's representing tangent as a quotient of 2. Quotient is the answer to a division problem. Quotient of 2 of the other functions. Okay. At the same time, since cotangent is the reciprocal of tangent, you should be able to guess that it's equal to cosine over sine. So in a way, we could represent every one of the trig functions just in terms of sine and cosine. Now, the next thing I want to go over is the Pythagorean identities. There are 3 of them, but really, I can honestly say I remember one very well, and then I can figure the other 2 out. It's also going to show relationship here. If you remember when we set up the unit circle, we had this idea that the hypotenuse is 1, and we had x and we had y, and so we stated that based on how we're going to do everything, so if this is my theta, then the sine of theta is equal to y, the cosine of theta is equal to x, and we also said that the tangent of theta was y over x, but I want to focus on these 2 because we're going to turn this into a Pythagorean identity. So Pythagorean, as in Pythagorean theorem. And you would agree from looking at this, I hope, that x squared plus y squared is equal to 1 squared, right? If we do square each of the legs and add them together, it gives us the hypotenuse squared. Well, if I do a substitution for this now, I'd have cosine squared theta plus sine squared theta is equal to 1, okay? And if you look, the way it's usually said is sine squared plus cosine squared equals 1. Of the same angle. That's always going to be true. Whether I'm in a unit circle and I have a triangle there, or anytime, as long as I have one angle that I'm taking sine squared of and cosine squared, it will always equal 1. This is huge. This is one of the single biggest things that when you go into calculus, you will use that often. And so I just say know that one. So sine squared plus cosine squared, I know I wrote it in the other order, is equal to 1. Now the other 2 Pythagorean identities, I think I just get out of this. So let me erase and start over. If I say that sine squared theta plus cosine squared theta is equal to 1. What would happen if I divided everybody through by sine squared? When I do sine squared divided by sine squared, I get 1. When I do cosine squared divided by sine squared, I get cotangent squared. And when I do 1 divided by sine squared, I get cosecant squared. That's a trig identity. It's a trig Pythagorean identity. At the same time, what if I went through and I divided everything here by cosine squared? Sine squared divided by cosine squared would be tangent squared. Cosine squared divided by cosine squared would be 1. And 1 divided by cosine squared is equal to secant squared. Now, if you ask me just off the top of my head, I know there's a relationship between tangent squared and secant squared. I never remember who has the plus 1. So I have to always start with sine squared plus cosine squared to equal 1. I know there's a relationship between cotangent squared and cosecant squared, but again, I never remember what has the plus 1. But to me, I don't have to. I don't have to memorize that because it's something that I can figure out very quickly. On the board in class, sometimes you'll notice I'll totally even leave out the angles. The angle is important, but a lot of times I'll just write it as sine squared plus cosine squared equals 1. I should always include the angle. You should always include the angle, whether it's an x or a theta, because it has to be the same angle. But a lot of times, just if I'm trying to figure things out, I'll just leave it like that. And then say, oh, divide everything through by sine squared. So that gives me 1 plus cotangent squared equals cosecant squared. Oh, divide everything through by cosine squared. And I'd say, oh, that gives me tangent squared plus 1 equals secant squared. This is my shortcut way of doing it. Okay, I do that for work, but in my final answers, I would always include an angle. So that's the first few of the trig identities. Know those well.